Hi guys, welcome to my YouTube channel, Learn Physics with IBM. And today I would like to take you to part 15 of solved past paper questions. Do not forget to share the documents in this video description. Do not forget to download the documents, print and follow the documents, follow the learning materials when you have a hard copy of yourself. The documents are entirely free. They are not for sale. They're just entirely free. Download the documents, follow the videos, and learn from the videos. Practice as you prepare for your exams. So we are dealing with the kinematics and dynamics, and I think this is going to be part 15. Most probably the second last part of kinematics and dynamics. Remember, I decided not to split kinematics and dynamics because the multiple choice questions overlap so much, so I couldn't really separate kinematics and dynamics questions. So without wasting time, I would like to take you to the past paper questions so that we start solving them. Okay, so I think in part 14 we stopped on this question here on page 135. So in part 15 I want us to start from this same page. So this is part 15. I'll change the color of. Okay, so a student throws a ball in the positive direction vertically upwards. So the ball is moving, the initial direction of motion is vertically upwards, that is against gravity. So the positive direction is the direction where it is moving vertically upwards. So the velocity is positive if it is moving vertically upwards, but remember the velocity decreases. So the velocity decreases. And if the velocity decreases, if I was to sketch a graph for the first part when it is moving upwards, velocity against time, so the velocity graph goes downwards. So that means the acceleration is negative. If it is a velocity time graph, it will be down going towards the zero axis or towards the x-axis. So it means initially the acceleration is negative. So the ball makes an elastic collision. That means when it makes collision, the velocity, there is a change in direction because it rebounds. But then since it is elastic, it again regains the same velocity but in another direction. So if I want to complete the velocity time graph, I will draw another line parallel to this one. So I will draw another line parallel to that one. I don't know why it's refusing to go away. Sorry about that. So I will draw a velocity time graph. So when it is going upwards, the velocity is decreasing. Then there's change in direction in a very short. Of course, when it hits the ceiling, then there's going to be change in velocity. Of course, it may not reach the ceiling with zero velocity, so I will not make the graph touch the zero axis. So there's a rapid change in velocity, so I will draw a vertical line here, and then I will draw a line parallel to the first one because it is again moving in the opposite direction but with the same acceleration in magnitude. So a graph of velocity against time may look somehow like that. In the first part, the velocity is decreasing. In the next part, the velocity is increasing, but in the opposite direction. So since the initial direction was upwards, the acceleration is always negative. Even when you look at these lines, the gradients are negative. So it means A and B are going to be wrong because they are showing a positive acceleration. So the ball makes an elastic collision with the ceiling. Because it's elastic, it moves with the same speed afterwards. Or it means it moves with the same rate of increase in speed in the opposite direction. The speed with which, no, it is an elastic collision. It means the speed with which it hits the wall is the same speed with which it leaves. So the graph should start from somewhere here. If it hits with this speed here, it should leave with almost the same speed. So I have the problem is with my eraser. It doesn't respond very well. I need suggestions for which applications I can use for recording these videos, because Samsung Notes was disabled for for computers. It's only for Apple phones. So I need to find another application. I tried Evernote. It was not good, so I gave up on it. So if it reaches the ceiling with this velocity here, then it should rebound with the same velocity because the collision is elastic. So I draw a straight line at this point here. So I'll just make a vertical line here. So the line is like this. Let me choose a different color. Okay. So it means the acceleration must be negative. It rebounds and accelerates back to the student's hand in a time of 1.2 seconds. Which graph best represents the acceleration of the ball from the moment it leaves the hand to the instant just before it returns to the ground? If air resistance is negligible, the acceleration is going to be constant. That is number one. No, unless apart from the point of rebounding where there is a rapid change in velocity and direction. So that is the only point where the acceleration will just change, but elsewhere it will be constant. That's why you see most of the parts of the graphs are constant. So at the point of the contact with the ceiling, the velocity rapidly changes from a certain value to zero, then back to a certain value. So we must have a spike. And if the velocity rapidly changes from a certain value to zero, then to another value which is negative, that means there is a bigger change in the velocity from a certain value to zero, and then from that value from zero back to the same value with which it hits the ceiling. So that means the acceleration rapidly increases at that point. Remember, acceleration is change in velocity over time. On hitting the ceiling, there is a rapid change in velocity from a certain value to zero, and then from zero to a certain value. So the spike must be showing an increase in acceleration because the change in velocity becomes bigger at that point. So that means the spike must must show an increase in acceleration. So the answer is going to be D as opposed to C. C shows that the spike is showing a decrease in acceleration, which means there's a smaller change in velocity. It is supposed to be a rapid increase in velocity. So the rapid increase in the velocity in the negative direction gives us a spike, which shows an increase in acceleration. So the spike must be away from the x-axis. So the answer is D. A moving body undergoes uniform acceleration while traveling in a straight line between points x, y, and z. The distance x, y, and y, z are both 40 meters. The time to travel from x to y is 12 seconds, and from y to z is 6 seconds. What is the acceleration of the body? Since the acceleration is uniform, then equations of motion can apply. I'll first sketch this. So I'll just sketch this for us to visualize. If this is x, and this is y, and this is z. Remember, the distance between each of them is 40 meters. It takes 12 seconds here. It takes 6 seconds here. Let's say it starts from here, and the initial velocity here is going to be u. The initial velocity there is going to be u. So I'm going to use s equals to ut plus a half at squared. So if we consider it reaching a position, reaching y, let the velocity at y be vy, and the velocity at z will be vz. Okay. So if we consider it starting from x and covering a distance of 40 meters to reach point y, then I'm using s is equal to ut plus a half at squared. So s will be 40. This will be equal to initial velocity is u times the time it takes is 12, so it becomes 12u. then plus, because it's an acceleration, it is plus a half times the acceleration times the time it takes, which is 12, but this is squared. So when I simplify this, I have that 40 equals to 12u plus 144 divided by 2. 12 squared is 144 divided by 2. I think that is 72. 12 squared divided by 2. So that is 72 times a. So that is going to be one equation. Then the second equation, I'm going to consider it again starting from the same position x, but this time reaching z. So the distance is going to be 40 plus 40, which is 80. The time is going to be 12 plus 6, which is 18. So it is 18 seconds times u plus a half times the acceleration. The time is 18 squared. So that is 18 squared. So this means 80 is going to be equal to 18u plus 18 squared divided by 2 is 162. So this is going to be 162 times a. That's 162 times a. So this is going to be the second equation. So we have two unknowns and two equations. So we shall just solve these two equations. Maybe the easiest way to solve these two equations, I'll multiply the first equation Let me multiply the first equation by 3 because I want to find I want to eliminate u, so that I have, if I multiply the first equation by 3 and the second equation by 2, I think I get the same thing. So this equation here, I'll multiply it by 3 and I'll multiply this equation by 2. Then I subtract the two equations. So 3 times 40, that is 120. 2 times 8, that is 160. So I have 160 minus 120 for the left hand side. Then 3 times 12, that is 36. 2 times 18, that is 36. When I subtract this one and this one, they cancel out. So this should be equal to 2 times 162. 2 times 162 is 324 times a minus 3 times 72. 3 times 72 is 216a. So minus 216 times a. So I'm trying to solve for a. So when you subtract here, you get, I make a the subject. So a is going to be 160 minus 120, that is 40, divided by 324 minus 1 minus that is 108. So I will press my calculator. 40 divided by the answer. This is 0.37. So this is going to be 0.37 meters per second squared. So the answer is going to be A. A particle of mass 2m and velocity v strikes a wall. The particle rebounds. If it rebounds, that means the collision is inelastic. So that means momentum is not going to be, momentum is conserved, but kinetic energy is not conserved. So for conservation of momentum, total momentum before colliding with the wall, total momentum before P1 is of course 2m times v. What is the possible change in the momentum of the ball during the collision? So because the collision is inelastic, of course whether the collision is elastic or inelastic, momentum is always conserved. That is for the whole system, but not for the ball. So the particle rebounds along the same path after colliding with the wall. The collision is inelastic. So if the collision is inelastic, we expect that the speed with which it rebounds, so of course it is the same particle 2m, let's say the speed with which it rebounds is v2. So if the collision is inelastic, it means v2 is going to be less than v, because the mass is the same. But since the collision is inelastic, some energy is lost on collision, so the speed decreases. Kinetic energy is lost, so the collision decreases. So since kinetic energy is lost, so it means the new velocity is less than the initial velocity. So that means the second momentum P2, which is going to be equal to twice m times v2, this momentum is going to be less than p1. So the second momentum is going to be less than p1. Therefore, the change in momentum of if the collision was elastic, the change in momentum would be, because the velocity v will be the same. If it was elastic, the change in momentum would be twice mv towards the wall minus negative 2 mv away from the wall. So this would be 4 mv. If the collision was elastic, then it will bounce with the same speed. But now that the collision is not elastic, it means the change in momentum must be less than 4 mv. The change in momentum must be less than 4 mv. So 4 mv is wrong. But again, because the change in momentum, of course, the change in momentum must also be greater than the p1. It will be less than 4 mv, but should be greater than the momentum before colliding with the wall. Because if it moves away, it has some speed, so it has some momentum. So the change in momentum must also be greater than the initial momentum before colliding with the wall, that is 2 mv. So it should be between 2 mv and 4 mv. So this one is wrong, this is wrong, so the answer is going to be C. If the collision was to be elastic, the momentum should be 3 mv. But the initial momentum towards the wall was 2 mv. So it means if it is inelastic and the final velocity is not the same as the initial velocity with which it collides with the wall, so it means the momentum of the ball after the total change in momentum should be between 2 mv and 4 mv. So the answer is C. Which defines the weight of a body? Of course, the weight is the pull of gravity on an object, so the answer is going to be B, the force of gravity on the body. A projectile is fired at an angle alpha to the horizontal at speed u as shown in the diagram. What will be the vertical and horizontal components of its velocity after a time t? So the horizontal, we shall resolve this, resolving u to the horizontal. U resolved to the horizontal would be u cos alpha. Resolving u to the vertical, of course, this is supposed to be u sine of alpha. So what will be the vertical and horizontal components of its velocity after a time t? So remember, velocity in the horizontal remains constant, so it will remain u cos alpha in the horizontal. Velocity in the horizontal remains constant throughout. So we ignore B and D. Considering horizontal, we ignore B and the velocity in the horizontal remains constant. But then the velocity in the vertical changes because there's an acceleration in the vertical. This one is constant because acceleration in the horizontal is 0. But velocity in the vertical will change, it will be u plus at. Velocity in the vertical will be equal to, initial velocity in the vertical is u sine of alpha. Because it's moving against gravity, acceleration in the vertical is equal to negative g. So this will be minus g times t. So the answer here is going to be C, u sine alpha minus gt. So the answer is C. The graph of velocity against time for an object moving in a straight line is shown. So it is velocity against time. Which of the following is the corresponding graph of displacement against time? Remember, a displacement against time, its gradient is the velocity. Gradient of displacement against time equals to the velocity. Okay, so let's first of all we can begin by inspection of the graphs. The first part shows of a velocity time graph. The first part is showing velocity is increasing uniformly. So it means the gradient should be increasing uniformly. So for this graph, this part is fine because the gradient is increasing up to this point. So here, velocity is increasing, which is seen on the graph. So here, it is showing that the velocity is constant. The velocity is here, velocity was increasing uniformly. And here it is showing that the velocity is 0. This part here, it is showing that velocity is equal to 0 because it's a horizontal line, the gradient is 0. The velocity here is 0, so this is out. Then this one, it is also showing velocity is increasing. So here the velocity is increasing for the first point of the graph. And here it is this is a straight line. It is a straight line if you compare with this one, it is a straight line. A straight line here means velocity is not 0, but it is constant. Velocity is constant. So we also ignore this one because on the graph, the velocity is increasing uniformly. We see it is a straight line, which shows velocity is increasing uniformly. For the second part, the velocity is constant. That should be a straight line for a displacement time graph. So this one is showing velocity is constant, which is fine. Of course, I've eliminated the B, I will not look at it. C is again a straight line up to here. You can see it is a straight line, which also shows velocity is constant. So it means that one cannot be used. Then let's see the last part. For velocity time graph, the last part is showing that the gradient should be, the velocity is decreasing. Here velocity is decreasing, but it is decreasing uniformly. So it should be a smooth curve. So, but there has been no change in direction. Yet this one is showing velocity is decreasing, but in the opposite. The gradient here is decreasing, but the gradient here is negative. That means there has been a change in direction. So this one is going to be wrong because the gradient is negative, which means a change in direction. The gradient is negative, which means negative velocity. It means a negative velocity. The gradient is negative, which means a negative velocity. Yet on the graph, we don't have a negative velocity. On the graph of velocity time graph, we don't have the negative velocity. So it means this graph is going to be out. Then let's check on this one. This one is a decreasing gradient, yes, and it is still positive. So here the velocity is decreasing because the gradient is decreasing. Gradient decreases, which means the velocity decreases, but still positive. So we are still in the same direction. So the answer is going to be C. Because the velocity is above the x-axis, it is still positive. So the gradient should never be negative. Okay, so the answer is C. A ball is released from rest and above a horizontal surface. The graph shows the variation with time of its velocity. Variation of time of its velocity. So areas x and y are equal. This is because the ball's acceleration is the same during its upward and downward motion. Of course, for a velocity time graph, the acceleration is the gradient. So here it is moving upwards in the first part, and here it is moving downwards because there's change in direction. So it is true that the acceleration is constant, but that's not the reason as to why the areas are equal. The area, remember, the area is equal to the displacement. So if this area is the same as this, it means the ball moves to the same. If it hits, it bounces from. It means the ball moves back to the same height from which it moved. So area is equal to the displacement. So area should be relating to distance. So this means this is wrong. The speed at which the ball leaves. So this is wrong. Area is the displacement. For one impact, the speed at which the ball hits the surface equals the speed at which it leaves. Area is the displacement or distance. The ball raises and falls through the same distance, so the answer is going to be D because the area will be the distance. If this area is the same as this, it means the ball raises and falls through the same distance. So area is the distance. So the answer is going to be D. Two blocks X and Y of masses M and 3M respectively are accelerated along a smooth horizontal surface by a force F applied to block X as shown. What is the magnitude of the force exerted by block X on block Y during the acceleration? Okay, so let the force on X, I'm going to call the force on block X by Y, I'll call it F on X by Y like that. And let the force on block Y by X be F on block Y by X like that. So the mass of this one is M and the mass of this one is 3M. Okay, then from Newton's, of course they have already taken away F from us and they called it accelerated along a smooth horizontal surface by a force F. So F is the force which is pushing, so they have already taken it away. So I'll use F resultant. Fr means resultant force by Newton's second law is given by Ma, which if I consider the mass X, the resultant force is Ma, so I will say M times A for X. This is for mass X. M times A for X is equal to the force acting on it towards the right hand side is F minus the force acting on it towards the left hand side is F X due to Y. So that is the resultant force on it. Then if I consider block Y, by Newton's second law, for block Y, the only force acting on it is Fy due to X. So by Newton's second law, the mass of this block is 3m. Because they are attached together, they are accelerated by the same acceleration, so times A is going to be equal to the only force acting on 3m is F on Y due to X. But I also want you to remember by Newton's third law, F X due to Y is the same as F on Y due to X. So they are the same. So I'll just call this one small letter f. Okay, so I'm going to combine the two equations, but remember these ones are opposite. They are equal but opposite. So I now have, what is the magnitude of the force exerted by block X on block Y during this acceleration. So I said, remember these two forces are equal but opposite. Okay, so I'm going to combine this equation here with this one here. So if I combine these two equations, I have that 4, I'm just going to add them because fxy and fyx, they are the same, it is just f. So I have that ma equals to capital F minus small f, and 3ma equals to small f. When I add the two equations, small f cancels. So it means capital F is going to be 4m ma. So the question is, what is the magnitude of the force exerted by block X on block Y? That is Fy on X. So I'll go back to the first equation, which says that ma is equal to F minus Fxy. No, 3ma equals to Fyx. I want this one here because that is the force exerted on block Y by block X. Fyx is the force exerted by X on Y. So I have that F on Y due to X is equal to 3 ma. So if because I want to express it in terms of F, I will combine it with this equation here. So I will divide by F. So divide here by F, divide here by F, I mean by 4ma. So ma cancels. So it means that F on Y due to X is going to be 3 capital F divided by 4. So the answer is going to be D. It's quite technical, but the answer is D. A car with a front wheel drive accelerates in the direction shown. A car with front wheel drive accelerates in the direction shown. Which diagram best shows the direction of the total force exerted by the rod on the front wheels? Total force. So since the car has a front wheel drive, so the wheel rotates in a clockwise direction. So if the wheel rotates in a clockwise direction, like this, it means the friction is the other way around. I'll increase the thickness slightly. So it means the friction is going to be in this direction. If the wheel rotates clockwise, the friction is going to be in that direction. So this is going to be the friction force. Of course, there's a normal reaction force at the point of contact. There is normal reaction force, which I'm going to call N. So it means the resultant of these two forces must be a force which is between them here. So the question is, which diagram best shows the direction of the total force? So this is the total or the resultant. Total force exerted by the rod on the front wheel. So the answer is going to be B, simply because if it is a front wheel drive, the wheel rotates in this direction, which is clockwise. That means the friction is the other way around, which is into the right. But there's a normal reaction force, so the resultant of these two is between them here. So the answer is most likely going to be B. Remember I said the front wheel rotates clockwise. So the friction is to the right hand side. A ball of mass 2 kilograms traveling at 80 meters per second strikes a ball of mass 4 kilograms. Traveling at 2 meters per second, both balls are moving along the same straight line as shown. After collision, both balls move at the same velocity v, so they are moving with a common velocity. What is the magnitude of the velocity? So that is just conservation of momentum. Remember, momentum is mass times velocity. Total momentum before they collide. Velocity is to the right positive. They are all to the right, so it is all positive. So total momentum before, we have 2 times 8 plus 4 times 2, that is total momentum before collision, should be equal to total momentum after collision. Since they stick together, the total momentum, the total mass is 6, then times the common velocity v. So we have 16 plus 8, that is 24. So v is going to be 24 divided by 6, which is going to be 4 meters per second. So the answer is A. The ball falls from rest through air and eventually reaches constant velocity. So it means the acceleration must be decreasing. So the graph of force for this fall, force x and y vary with time as shown. Of course, this force y, let's say the ball is falling in air. So the weight remains constant, and the other forces acting are going to be the drag force or the air resistance. So this is air resistance, and the other force is going to be maybe the upthrust. The other force could be the upthrust. So the weight remains constant. The force due to air resistance increases with time. So the resultant force is going to be equal to, no, let me just ignore the upthrust because it may be very small. So the resultant force is going to be the weight minus the drag force or the force due to air resistance, which is the drag or the viscous drag, sometimes represented by V. So this one increases with time. The force, the viscous drag increases with time, but then as it increases, a point reaches where when the viscous drag is the same as the weight, it means the velocity remains constant at that point. So it means the viscous drag will remain constant when it is equal to the weight. But that means if the viscous drag is increasing, the resultant force must be decreasing. So that means the resultant force must be going to 0. When the viscous drag equals to the weight, the resultant force is going to be 0. So this means force Y must be the resultant force, and force X is most likely going to be the drag force, because the drag force increases until it is equal to the weight. It remains constant at that point where the acceleration becomes 0. The resultant force decreases as the force due to air resistance increases. So let's check what are forces X and Y. So we have said X is going to be the air resistance force, not the upthrust, and Y is going to be the resultant force. So the answer is going to be A. The weight and the upthrust will be constant. After, even the upthrust could be very small. So I said as it falls, air resistance goes on increasing with time, but then it will stop increasing when it is equal to the weight. That's why you see this graph shows an increase in force, which is almost becoming constant. When it becomes horizontal, here the weight is equal to the air resistance or the drag force. So this is air resistance. And as the drag force increases, the resultant force decreases, because the resultant force is the weight minus the drag force. Because the drag force is becoming bigger, this difference is becoming smaller. So the other graph must be resultant force. A motorist traveling at 10 meters per second can bring his car to rest in a distance of 10 meters. If he had been traveling at 30 meters per second, in what distance could he bring the car to rest using the same braking force? So he's using the same braking force. Okay. So a motorist traveling at 10 meters per second can bring his car to rest in a distance of 10 meters. So if he's using the same braking force, he's going to be using the same acceleration. So I'll use v squared equals to u squared plus 2as. because it's using the same braking force, it's going to use the same deceleration. So final velocity is going to be 0 squared, initial velocity is 10 squared minus 2 times the acceleration times 10. So it means the deceleration of this motorist is going to be 100 divided by 20, which is, so the deceleration is going to be 100 divided by 20, that is 2, that is going to be 5 meters per second squared. So the deceleration is 5 meters per second squared. Then in what distance could he bring the car to rest using the same braking force? So he's using the same deceleration, because force is equal to mass times acceleration. If it's the same braking force, then it's the same deceleration. So using the same equation again, 0 squared is going to be equal to 30 squared minus 2 times 5 times the distance s. So it means s is going to be 900 divided by 10. 900 divided by 10, which is going to give us 90 meters. So I'm using a minus because it is a deceleration. It is coming to rest, is applying brakes, so it's coming to rest. So that's why I'm putting a minus here. So the answer here is going to be 90 meters. The graph relates to the motion of a falling body. So which is a correct description of the graph? So it is a falling body. So we know for a falling body, if the graph is becoming horizontal, there are two things. Either the air resistance is becoming equal to the weight, so y could be force due to air resistance, where it is becoming equal to the weight, or y could be velocity, where it is becoming constant, the body is reaching terminal velocity. So which is the correct description of the graph? Y is the distance and air resistance is negligible. So this can't be distance. Y is the distance and air resistance is not negligible. Y is not the distance. Y can be speed, but air resistance cannot be negligible, because if the air resistance was negligible, then this would be a straight line. So the answer is going to be D. Because if y is speed, as speed increases, air resistance also increases. If air resistance increases, then the drag force increases, so a point reaches at some point, the weight of the body will be equal to the air resistance. At that point, the resultant force is equal to 0, the acceleration is equal to 0, the velocity becomes constant. And this velocity, we have been calling it terminal velocity. So we see that the velocity is becoming constant, so the y is supposed to be speed and air resistance is not negligible. Which graph represents the motion of a car that is traveling along a straight road with uniformly increasing velocity? If it is uniformly increasing the velocity, remember the gradient is the acceleration. So uniformly increasing velocity is sketched like this. Uniformly increasing, the velocity is increasing by equal amounts in equal time intervals. That is a straight line like that. So this straight line gives us a constant gradient for acceleration. So it should be a horizontal line. C and B are out. So D is out because D is displacement against time. So the answer here is going to be A. Why is D out? D gives us zero velocity because the gradient of a displacement time graph is the velocity. A horizontal line gives us zero gradient, so this is showing zero velocity, yet the velocity is increasing uniformly. But A is correct because for a uniformly increasing velocity, the acceleration is constant. C is also wrong because C is showing that the velocity is constant because it's a straight line. A is showing an acceleration which is increasing because it's acceleration against time, yet the acceleration for uniformly increasing speed is constant. So the answer is A. A stone is thrown upwards from the top of a cliff. After reaching its maximum height, it falls past the cliff top and into the sea. The graph shows how the vertical velocity v of the stone varies with time t after being thrown upwards. R and S are the magnitudes of the areas of the two triangles. What is the height of the cliff top above the sea? So the stone is thrown upwards. So it is thrown, let's say this is the cliff. It is thrown upwards. After reaching maximum height, it falls past the cliff, so it goes down past the cliff and into the sea. So this is the sea. Okay. The graph shows how the vertical velocity of the stone varies with time. So for the first part, when it is going upwards, it is S. Because here it is at maximum height when V is 0. This is maximum height. Then when it is falling down, the speed is increasing in the opposite direction. So this side is R. This side is R. Here it is S. This side is R. So what is the height of the cliff top above the sea? So we want this height here. So by common sense, the height h is going to be R minus S. So the answer is D. A wooden block of mass 0.6 kilograms is on a rough horizontal surface. A force of 12 newtons is applied to the block and it accelerates at 4 meters per second squared. What is the magnitude of the frictional force acting on the block? Magnitude of the frictional force acting on the block. So if it is moving to the right, then the friction must be to the left. And I'll call this friction small letter f. Okay, by Newton's second law, the resultant force capital F is m times A, which is going to be equal to 12 minus the frictional force small f. So the mass is 0.6 times the acceleration, which is 4, should be equal to 12 minus f. So what is f? F is going to be 12 minus open brackets 0.6 times 4. So F is going to be 9.6 newtons. So the answer is B. A body initial at rest explodes into two masses, m1 and m2, that move apart with speed v1 and v2 respectively. What is the ratio v1 over v2? So we have answered a similar question. Before it explodes, initial momentum is 0. Since they move apart, one momentum is positive, another momentum is negative. So when we add them, the first one will be m1 v1 plus negative m2 v2. Momentum of one, momentum of the other, they're in opposite direction, so it's plus a negative. So this means m1 v1 is equal to m2 v2. So v1 over v2 is equal to m2 over m1. So the answer is going to be B. Okay, a car is traveling with a uniform acceleration along a straight road. The road has marker posts every 100 meters. When the car passes one post, it has a speed of 10 meters per second, and when it passes the next post, it has speed of 20 meters per second. So the road marks have 100 meters apart. So I'll just try to sketch this. This is the first post, the second post, and the distance is 100 meters. So here it is at a speed of 10 meters per second, and here it is at a speed of 20 meters per second. So if we assume the acceleration is constant, I will use the equations of motions, especially v squared is equal to u squared plus 2as. So final velocity is 20. 20 squared should be equal to 10 squared. Because it is accelerating, this is still positive. 2 times the acceleration times the distance apart, which is 100 meters. So I'll just collect the like terms. 20 squared on the left minus 10 squared on taking it to the left, divide by 200. So that is 1.5. So the acceleration is going to be 1.5 meters per second squared. So the answer is B. I need to check for a shouting color. A tennis ball is released from rest. Initial velocity 0 at the top of a tall building. Which graph best represents the variation with time t of the acceleration a of the ball as it falls, assuming that the effects of air resistance are appreciable? So in other words, we cannot ignore air resistance. That's what that means. Okay. So since it is falling in air, for an object falling in air, the weight remains constant. The force due to air resistance increases. So if the resultant force is equal to the weight minus the air resistance, if the air resistance increases, this difference becomes smaller. It means the resultant force decreases. But remember, the resultant force is mass times acceleration. So if the resultant force decreases, the acceleration must decrease. So which graph best represents the variation with the time of the acceleration? So this one is wrong. It is showing acceleration is constant. This one is wrong. It is showing acceleration increases. Here, acceleration is constant. Here it is showing acceleration increases, which makes it wrong. This one is also wrong because even here the acceleration is increases and then becomes constant. But the answer is going to be D because the acceleration decreases, it goes to 0. So the answer is automatically D. A motorcycle stunt rider moving horizontally takes off from a point 1.25 meters above the ground, landing 10 meters away as shown. So what was the speed at takeoff? So this is a projectile. The stunt is a projectile. So if we consider, let's consider vertical motion first. If I consider vertical motion, I will be able to get the time. So considering vertical motion, S in the vertical is equal to initial velocity in the vertical times t plus a half acceleration in the vertical times t squared. Initial velocity in the vertical is 0 because the motion was horizontal. Acceleration in the vertical is going to be g. So in the vertical, it moves a distance of 1.25. So 1.25 meters is equal to a half times g, which is 9.81, then times t squared. So this gives us t as 2 times 1 point to be the square root of 2 times 1.25 divided by 9.81. That is t. Now I want the speed at takeoff. So I'm going to consider now horizontal motion, and I'll use s in the horizontal. So s in the x, meaning s in the horizontal is equal to initial velocity in the horizontal times t plus a half acceleration in the horizontal times t squared. But I want you to note that acceleration in the horizontal is 0 because there is no force acting in the horizontal. And initial velocity in the horizontal is what we want to find. Initial velocity in the horizontal, let it be just u. Of course, the time is the same because time is a scalar. But in the horizontal, it moves a distance of 10 meters. So 10 meters, 10 is going to be equal to u times t, which is the square root of 2 times 1.25 divided by 9.81. So I'm just going to press here the calculator. 2 times 1.25 divided by 9.81, square root of the answer. Then I'll say 10 divided by the answer because I'm making you the subject. So that gives me 19.81. So u is 19.81, which is approximately 20. So the answer is going to be D. A ball folds vertically and bounces on the ground. The following statements are about the forces acting while the ball is in contact with the ground. So while the ball is in contact with the ground, number one, its weight, the pull of the earth onto the ball is the weight. Then number two, the pull of the ball on the earth, that is the normal reaction. Those are the forces acting when it is in contact. The force that the ball exerts on the ground is always equal to the weight of the ball. Which statement is correct? The following statements are about the forces acting while the ball is in contact. The force that the ball exerts on the ground is always equal. So this part here is not true because the ball bounces. So it is not equal. The force that the ball exerts on the ground is always equal in magnitude and opposite in direction to the force that the ground exerts on the ball. This makes sense because they're in opposite direction. This one was just saying the force that the ball exerts on the ground is always equal to the weight of the ball. It's not always equal to the weight of the ball, but the force that the ball exerts on the ground is always equal in magnitude and opposite in direction to the force the ground exerts on the ball. This is Newton's third law. So the answer is automatically B, according to Newton's third law. The diagram shows a situation just before a head-on collision. A lorry of mass 20,000 kilograms is traveling at 20 meters per second towards a car. So it mass 20,000, 20 meters per second, traveling towards a car of mass 900 kilograms at 30 meters per second towards the lorry. What is the magnitude of the total momentum? Magnitude of the total momentum. So since we know that momentum is mass times velocity, velocity is to the left, to the right positive, to the left negative. So the total momentum is going to be, for the first one, is going to be 20,000 times its speed, which is 20, plus for the other one is negative 900 times 30 because it is in the opposite direction. That's why I put a negative here. So that is the total. So 20,000, that is 20,000 times 20 minus 900 times 30. So that is 373,000 Newton seconds. So the answer is going to be A, 373 kilonewton seconds. Which feature of a graph allows acceleration to be determined? Of course, acceleration can be determined from a velocity time graph as the gradient or the slope. So the answer is automatically D. From a velocity against time graph, if it is a straight line, we know that the acceleration is equal to the gradient of a velocity time graph. So the answer is D. Which is not one of Newton's laws of motion? So you should be knowing the three Newton's laws of motion. Total momentum of a system remains constant provided no external forces act. So this is not Newton's law of motion. This is the law of conservation of momentum. The rate of change of momentum of a body is directly proportional to the external force acting. This is Newton's second law. If a body A exerts a force on body B, then B exerts an equal but opposite force on body A. This is Newton's third law. Action and reaction are equal but opposite. A body continues in a state of rest or uniform motion in a straight line unless acted upon by some external force. This is Newton's first law. So the first one is not Newton's law. A steel ball is falling at a constant speed in oil, which graph shows the variation with time of the gravitational potential EP and the kinetic energy EK. It is falling at a constant speed in oil. What does that mean? The kinetic energy must remain constant. But remember, it is falling. Remember, kinetic energy equals to a half mv squared, but the speed is constant, so kinetic energy must remain constant. That is a horizontal line. Potential energy is equal to mgh. It is falling. H is decreasing. Potential energy must be decreasing. But since h is not going to be decreasing uniformly, since the speed is decreasing, h is not going to be decreasing uniformly since the speed is decreasing, then this is not going to be a straight line. So first of all, we shall ignore, okay, it can be straight line because let's begin by ignoring where kinetic energy is not constant. We first eliminate C, kinetic energy should be constant. We ignore D, kinetic energy should be constant. Now we have to choose between A and B. If the ball is falling at a constant speed, okay, since the speed is constant, then it means h decreases with equal amounts. H will decrease uniformly, so the answer is automatically going to be B because the speed is constant. But if it was falling with a a decreasing speed, then it means it will not be a straight line. Or if it was falling with an increasing speed, then it will not be a straight line. It will actually be either A, no, because it will be falling with an increasing speed. Again, this will also not be a straight line. So the answer is this one, because for kinetic energy, speed is constant. The kinetic energy should not change. And if the speed remains constant, means the height decreases by equal amounts in equal time intervals. So it means the potential energy also decreases uniformly. So the answer is going to be B. An experiment is done to measure the acceleration of free fall of a body from rest. Free fall of a body from rest. Which measurements are needed? Of course, S equals to UT plus a half at squared. If it is falling, initial velocity is 0. So S is h equals to a half g t squared. So which measurements are needed? We want to measure the acceleration of free fall g. So we need the height, we need the time. So let's check. The height of fall and the time of fall, I think the answer is A. The height of the fall and the weight, we don't need the weight. The mass, we don't need the mass. The mass, we don't need the mass. The acceleration is not depending on the mass, it is depending on the height and t. And lastly, for this part 15, a cyclist is riding at a steady speed on a level road. According to Newton's third law, what is equal and opposite to the backward push of the back wheel on the road? According to Newton's third law, what is equal and opposite to the backward push? If it is a backward push, then the other one should be forward. It should be a forward push. So the tension is out, total air resistance is out, the force by the cyclist on the pedals, that is out. So it will be the forward push on the road on the back wheel. So because the force should be equal but opposite, So if there's a backward push of the wheel on the rod, then there should be a forward push on the wheel by the rod. So the answer is going to be B, the forward push of the rod on the back wheel. So the answer is going to be this one here. Okay, let's start the last part, which is going to be part 16 on this page here. So see you in part 16. I hope you have learned something from these videos. And in case of any mistake, do not hesitate to write a comment. I'll always respond to the comments. Do not forget to subscribe, share the documents. These are completely free. I was told some teachers are selling them, but just know these are completely free. They are printing my content and selling it to their students, which is really not fair at all. Therefore, share the documents with your friends, download, print, so that you follow the printed document as you watch the videos. Until next time, bye bye.